3.9. Is a big topic. It's called related rates. What does that mean? Two or more variables have rate of change. Their rate of change are related somehow through an equation, through some sort of relationship. Here's an example. I have a balloon and I pump air in the balloon. What changes? A lot. The surface area, the volume, the radius. All these three change in time. As more I continue pumping air in the balloon, the surface area increases, the radius increases, right? The volume increases, and these are all related rates. dr over dt, the rate of change of radius with respect to time, dv over dt, the rate of change of volume with respect to time, and ds over dt, the rate of change of surface area with respect to time. They're all related. They happen at the same time, and they happen in a relationship. That's what we mean related rates. It's a major topic. I can talk about this for at least a month. There are so many different applications. There is no way we can look at this topic for a month. So we're going to just start with several and look at several different situations. Of course, I'll let you choose. I can recommend the first one, and then we can choose anything else you want. Allow me to recommend the first one. Okay. I like to start with this one with a spotlight on the ground. Shines on the wall 12 meters away. So imagine that there is a flashlight or a spotlight right there on the floor where the podium computer is. And it says it's 12 meters away from a wall. Let's say it's 12 meters from there to here. Then it says if a man 2 meters tall, I'm not 2 meters tall, but walks from the spotlight towards the building at a speed of 1.6 meters per second, the distance covered changes at 1.6 meters per second. I walk from the spotlight is right behind me. I walk at 1.6 meters per second towards the building. How fast is the length of his shadow on the building decreasing when he's 4 meters from the building? So when I stand here and the spotlight is right at my feet, my shadow is huge on the wall. When I get closer and closer, my shadow on the wall decreases. So we're asked to determine how fast is the shadow decreasing at a particular instant. So let me show you the scenario. Okay, so this is problem 16 on page 248. The main idea before I draw the picture or pictures, the main idea is that in order to answer the problem, I have to create a relationship between two variables at least, maybe three, at least two variables, create a relationship like an equation, and then create another equation that relates their rates of change. That's the idea. Okay? So here's the picture. That's the wall. Here is the flashlight or spotlight, whatever. And here's the person initially. I can't draw a person, please forgive me. That's all I can do. See his shadow on the building, on the wall? Here is what happens when the person, the same height, is much closer. To the wall than initially, right? So the person is walking in this direction towards the wall. Obviously, initially, this is the height of the shadow, but then the person, the closer the person gets to the wall, the shorter the shadow on the wall becomes. Would you agree with the scenario? Okay, perfect. I'm going to say that this is y. I'm going to say that this is x. I denoted x, the distance covered by the person walking towards the wall. I have the length of the shadow of the person on the wall. That changes at every moment because the person walks towards the wall, right? Okay. And we read the problem one more time. A spotlight on the ground shines on the wall 12 meters away. Done. If a man 2 meters tall, okay, walks from the spotlight toward the building at a speed of 1.6 meters per second. I have to identify what this is. How fast is the length of the shadow on the building decreasing when the man is 4 meters away from the wall? First, we have to identify what 1.6 meters per second represents, and then we have to identify what the problem is asking us to do. What are we asked to find?
(1.6) would be the derivative of x.
Indeed. dx over dt, it's the rate of change of distance with respect to time. Good. This is what it's given to us. Excellent. Then, what is the problem asking us to determine?
It wants I guess y, not really d of y, but y and 4.
Let's read the question one more time. Perfect question. How fast is the length of his shadow on the building decreasing when blah, blah, blah?
So it actually wants the derivative of y.
Excellent. Correct. So we are given rate of change of time with distance with respect to time, which is 1.6. And they want us to determine how fast is my shadow decreasing when I move closer and closer to the wall. Now, this is when x is how long?
Sorry, the line you drew threw me out.
Yes, so this is how we evaluate. Because there is no, so if I have f prime of x, I can put f prime of whatever. But if I have dy over dx, I don't know where to put that. So we write this when x is. Because we can plug it in. There's nothing to plug in here. So this is basically this. When x is, careful, I'm here. Exactly. Now, one very important remark. This is only at the very, very end. Do not put 8 anywhere but at the very final step. So this you can forget about. You have to determine an equation between x and y. You have to find dy over dt. And when you're done, you plug in 8. So please remember, do not include that in any of your calculations. Okay, so the whole problem reduces to what? Reduces to creating an equation between x, with having x in it and y. Once I have an expression or an equation that relates x to y, then I differentiate that, I'm done, and I plug in numbers. So here's the scenario. At any particular instant, that's all I have. What does this mean? I'm telling you something. What am I telling you? I'm telling you that the purple triangle and the pink triangle are the last sides are proportional. But before I do that, I have to show that the tiny triangle and the big triangle are similar. Very good. So A, B, C, D, E, triangle ABC is similar to triangle ADE. Why? They both have a right angle. I have to show pairs of angles that are congruent or equal. They have the same common angle. Therefore, B and D must be the same, because otherwise they will not add up to 180. So knowing that these two angles have congruent pairs of angles, we can immediately conclude that they are similar. And you can say, so what? And Colby already gave us the answer. Why is it so important? Because now I can write proportions with their sides. But I have to be very careful how I write those proportions. Everything that I'm going to write at the top has to come from one triangle, not mix and match. Everything I write at the bottom has to come from the other triangle. But again, in a particular order, not just anything. So here's how we do it. I start with a common angle. You can start at any point you want, but I'm going to start with A. What is the opposite side of A in the small triangle? 2. What is the opposite side of the same angle in the big triangle? Excellent. There is nothing I can do to this because I don't have this and I don't have that. So the next one, I don't care. I finally reach this point, this angle. What is the opposite side of angle B in the small triangle?
X.
The corresponding congruent angle now. What is the side opposite to angle D in the big triangle? 12. Now I have a proportion. And this is the equation that I need that connects x to y. That's all I care about. I found an equation that connects x with y. And now I can find the equation that relates dx over dt to dy over dt, and that's what I want. Of course, I'm going to cross multiply, and I have xy equals 24. Now, remember, x and y are two functions of the third variable. What is the third variable and what functions are they? They are functions of
Time.
Of course, they're functions of time. I walk, I change the distance with respect to time. I walk, my shadow is changing with respect to time. Very good. So let's differentiate both sides. Maria, do I talk too much? I'm sorry.
No.
Is it me?
No.
Are you okay? Do you need me to do anything?
Just a long night. Yeah.
So let's differentiate. It's a product. We have to use the product rule, which means I have to write a sum of two terms. We differentiate the first function, and no, we do not get 1, but we get over dt, excellent, times y, plus x times, excellent. What are we after again? We're after, we are going to solve for this and then plug in 8. So x dy over dt equals negative y dx over dt. Therefore, dy over dt equals negative y over x dx over dt. I found my function, I found its derivative, and now I'm ready to plug in everything you want. Let's see what we have and let's see what we don't have. So now this is x equals 8 meters. So this is 8. This is what we were given, this one number, 1.6. And now I'm having, I have to determine y. But look at the equation, x times y equals 24, and x is 8. What could y be when x is 8? Right? Correct? Good. So when x is 8, y must be 3. So this is 3. And of course it's decreasing, which is given by the negative sign. So we have 3 times 1.6 and divided by 8. I got 0.6, of course, with minus in front. And I'm waiting for you to give me the measurement unit. It's the rate of change of a height with respect to time, or a distance with respect to time. Yes, but it's, yes, you're right, but it's meters. Yeah, yeah. Very good. So this is our first problem on related rates. So let's summarize what the steps that we went through. Number 1, we read the problem at least once, maybe twice, as many times as we need to understand what is given, what we're asked to determine. We looked at the picture or a figure giving us the scenario, discussing what is given in the problem, what rate is given, and how do I create an equation that relates 2 or maybe 3 different variables. After I determined the equation, I differentiated, knowing that these were functions that were functions of time. So when we differentiated, we kept in mind that x prime is not 1, but it's dx over dt. Y prime is not 1, but it's dy over dt. We solved for what we were asked to determine, and we plugged in the numbers, and that was it. Okay, many steps though. Okay, so I'd like to choose the next one if you'd like, but at some point in time, I'd like to look at the cone situation. So we looked at a similar triangle situation. Now I would like to look at the volume of a cone to see what we're asked to determine. Is that okay? Okay, so let's read the problem. Gravel is being dumped from a conveyor belt at a rate of, so this is 27 on page 249. 27 on 249. And we're told that the rate, gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. 30 cubic feet per minute. And I want to know what this is. I can read on or stop for a moment and think. The measurement unit I see tells me exactly what this represents. What does it represent? Look at the measurement unit and say, oh, I know. Say it again. Oh, we have to write D. Yes? So I agree with D. I agree with DT, but I need the top. What do you think the top is? If the measurement unit is cubic feet, what could it be? Could it be distance? Could it be area? Could it be volume? What could it be? What do we measure in cubic feet? Indeed. It must be dV over dt, right? If I had 30 feet per minute, it's very clear. It's distance with respect to time. If I had square feet, it's definitely the change of what we measure in square feet.
Area?
Of course, with respect to time. But if I see cubic feet, it's absolutely clear. It must be. Agreed?
Yes.
Moving on. In such a way that it forms a pile in a shape of a cone whose base diameter and height are always equal. When I hear always equal, this is not some piece of information that I have to wait till the end to plug in. No. This has no bearing on anything. This is given to us at all times. They are dumping sand, whatever they're dumping, cement, whatever, doesn't matter, and it forms a cone, but at any point in time, the base diameter and the height are always equal. Always. The word always means always. I don't have to wait till the end. This is a piece of information given to us from the very beginning. Okay, how fast is the height of the pile increasing when the pile is 10 feet high? Okay, so I know I'm given the volume, actually the rate of change of volume with respect to time, which is 30 cubic feet per minute. I am also told that this is always equal to this, no matter what, at any point in time that it's carved in stone. And I'm asked to find, again, question, how fast is the height of the pile increasing when the pile is 10 feet high? So I need to identify the question.
You're trying to find the DH over DT.
Excellent. Absolutely. This is the question. How, when the height is 10 feet. And remember, that I cannot take into account. That has to wait till I find the function, I find the derivative, and then at the very end I plug in. In other words, this is the instant. This will be the instantaneous velocity when h is 10, or instantaneous rate of change when x is 10. I cannot use that. Good. What is our starting point? We know we have to relate to two functions of time. What are those functions of time that I have to relate them? The
Derivative of volume.
The volume is one function, and what else? It's a function of time. And what other function has to be related to the volume? The function called height, which is also a function of time. So I have the function called volume, and I have the function called height. I have to find the relationship between these two functions, and I have to differentiate that relationship to find a relationship between their rates of change. Okay, can anyone give us a relationship between the volume and its height? So let me refresh your memory on a couple of formulas. So the volume of a cylinder, this is a cylinder. You can say, wait a minute, what are you trying to do? We're talking about the cone. In a moment, I'll explain. The volume of a cylinder is the area of the base times the height. The area of the base is pi r squared times the height, which is h. And I want you to remember these two formulas together. The volume of a cone is the same but divided by 3. It's pi r squared height divided by 3. So please remember these two formulas together. Good. So I found the function that relates, I found the relationship that relates the function v, which is a function of time, so pi over 3 r squared times h. So this is one function and this is the other function. They are both functions of time. I realize now that I also have something extra in here. But I am told that at any point in time, the height and the diameter will stay the same, will stay equal. So I have to get rid of this. It's in the way, I don't know anything about it other than the fact that the height is the same with
2r.
Very good. Of course, I'm going to solve for r to replace it in here. So how much is r? H over 2. Good. So I just plug it in. So the volume equals pi over 3 h squared over 4 times h. Or the volume equals pi over 12 h cubed. I accomplish a major task. I created an equation, a relationship between two functions of time. Function v, volume, and function h, height. Both functions of time. Good. After I determine this, what is my next step? Of course, because I'm interested in the h over dt. Good. So when we differentiate the left, we have to differentiate the right. The left derivative of the volume is
30.
dv over dt. On the right-hand side, we can plug in any numbers till the very end. Good. What now?
Could be 3 pi over 4.
Over 12, which is pi over 4. Very good. Excellent. That's good. Perfect. You can write it into steps. Times h to which power? Excellent. Times, remember, age is not a variable. Age is a function of time. So times,
dh over dt.
that's it. Times the h over dt. So I brought 3 down. I simplified 3 pi over 12, and I got pi over 4. I subtracted 1 from the power, and I differentiated the inner function. Are we comfortable with this relationship? Is this clear? Yes, everyone? Yes? Okay. I will solve for what I'm interested in. Yes, please, Reese.
I have a question about where h squared would work from.
This one?
The one up top.
I squared. I have to square r squared. I get, so h squared over 2 squared.
I just lost it.
I'm sorry, forgive me. So I replaced r squared by squaring this. So it's h squared over 4, and then I multiply these two to get that. I multiply these two to get this. Is everything else okay?
Where the 4 came from.
Is everything else okay
Yes.
after that? Okay, perfect. Which quantity am I after?
dh/dt.
Correct. So therefore, dH over dt is dv over dt, do not separate that. Now it's together, divided by pi over 4 times h squared. So I divided both sides by this. All I have to do now is plug in numbers. When, what was it? When age is 10 feet. Indeed, dv over dt is given to us as 30. Pi over 4 is pi over 4, and h squared is 100. I will simplify, and I have 6 divided by 5 pi. And I get 6 divided by, put parentheses, or divide by 5, and then further divide by pi. Be careful how you put this in. I got 0.38 approximately. I need the measurement unit. It's the rate of change of distance with respect to time. Rate of change of distance with respect to time.
So it would be feet. I'm gonna say feet to cube per minute. Oh no, it's not.
It's distance,
Oh,
right? It's the height. Since it's the height, it's going to be feet. If it's dA over dt, it would be feet squared per minute. If it's dV over dt, it would be cubic feet per minute. But if it's distance with respect to time, it will be just feet per minute. Is that okay, everyone? Okay. Any questions? I know I have 6 more minutes. I will stop, but let's at least get this started. Yes, 15. Two cars start moving from the same point. One travels south at 60 miles an hour, and the other one travels west at 25 miles an hour. At what rate is the distance? So they do this. At what rate is the distance between them increasing 2 hours later? So south at 60, west at 25 miles an hour. So this is 15 on 248. South at 60 miles per hour, west at 25 miles per hour. At some point in time, they're here, and this is their distance. I'm going to call it W. Okay. Let's read the problem one more time. Two cars start moving from the same point. One travels south at 60 miles an hour, the other one west at 25. At what rate is the distance between the cars increasing 2 hours later? 2 hours later. What am I asked to determine in this problem?
dw over dt.
Of course. When time is 2 hours, do not even look at this. Do not do that. I'm just making a point. I just want to trigger your memory. forever, that this is not to be dealt with now, this is not to be put in any equation, just the very last step. After I find an equation between all the variables, after I differentiate both sides, with respect to time, of course, and I solve for dw over dt, and only then I put time equals 2 hours. Right now it means nothing. Okay, I'm gonna call this x, of course I'm gonna call this y, and obviously I have to come up with an equation that eventually I can differentiate to get dw over dt. Any suggestions here? Say it again. Say it again.
Do you like Pythagorean theorem?
Of course. Excellent. How do I write it? And when my students say Pythagorean theorem, I'm going to say that you're going to say that. They say, oh, it's easy. A squared plus b squared equals c squared. No. The longest side squared, which can be denoted by anything you want, is the sum of the squares of the legs. Right? A squared equals b squared plus c squared doesn't mean anything. Right? The longest side squared is the sum of the squares of the legs. Okay, perfect. Excellent. Thank you. So what do I write?
X squared plus y squared equals w squared.
Good. And I'll stop. I know I only have 1 minute. So all these three variables are not variables. All these three, x, y, and w, are functions of
Time.
correct. So let's just differentiate and we'll stop. Please differentiate.
So that 2x times dx dt
Excellent.
plus 2y dy dt
Excellent.
2w dw dt.
Excellent. So please solve for the w over dt after you simplify both sides by 2, get rid of those constants. And then we'll take it from here on Thursday and finish it up to calculate dw over dt.